So we're going to finish things off with an application section, dealing with a couple of topics here. Well, I should say a few. The first is optimization, and optimization is when you're trying to find like the maximum or minimum value of a function built in an application setting. For instance, you might be building a water reservoir for a fire truck and trying to figure out the maximum volume that a water basin can have, or the water reservoir could have, um, but still, maybe working under constraints of, having enough room to fit your firefighter tools, or perhaps, like one of my friends does. He works for TACOM, which is a contractor for the military, and they build all sorts of things. And one of the things that they build are the Humvees. And he says that he does optimization all the time. He has to take data, in Excel files and construct functions or models for them in order to figure out like what the minimum cost would be to manufacture a Humvee with a specific thickness of armor, around the whole thing. And so this idea of, minimizing a cost or maximizing a revenue, anytime you're looking for the biggest or smallest value of a function, you're doing optimization. And so we're going to do just that with a nod to our 3-week, well, she's been with us for 3 weeks now. We have a Corgi puppy, and so it's our second Corgi, and we named her Pretzel. So our first Corgi, her name is Toast. All right, so in this example, we want to figure out how many pretzels have to be sold in order to maximize profit. Now it says here the profit that a vendor makes by selling X pretzels is given by this function. Okay, so this is a case where the model or the function is already provided to us. So let's find the number of pretzels that must be sold to maximize profit. Well, first of all, I want to address why there is a maximum profit. This is a quadratic function, in which case the value of a is negative. So if we were to look at this function's graph, we would see a parabola that opens down. And so there truly is, in fact, a maximum. Now, do recall that the maximum is also where the vertex is at, so h comma k. Now, when it's referring to the number of pretzels, we want to figure out which of these values, are we really looking for. Now, if you go back to the first sentence, it mentions x pretzels. Okay, so what it really wants from this vertex is the value of h. Okay, because that's a particular x value, and our x values in this case represent pretzels. All right. In other words, if you were to maybe superimpose this with a coordinate plane, going along the x-axis would be our different values of pretzel amounts, and then going along the y-axis would be the corresponding profit. And we would be interested in this tick mark. All right, so to answer this question, we'll use the formula negative b over 2a. Our value of b is 2400. So that's negative 2400 all over 2 times negative 4. And if you punch this into your calculator, make sure to use an extra set of parentheses, because what you should get for our answer is 300 pretzels. Now, if we wanted to figure out the maximum value of the profit, what would we do to figure that out? So to figure out the max profit, you would take the 300 and plug it into this profit function. But it doesn't ask us for that. It just wants to know how many pretzels need to be sold in order to get that maximum profit. All right, don't you feel bad for that pretzel over there in the meme? It's under assault. Help. All right. So that was an instance where the model was already provided for us. From here on out, we will mix some ideas together to form models ourselves. So the other topic here is the law of demand. It says here that revenue R is defined as the amount of money received from the sale of an item. Okay, so if you've ever had to sell Little Caesar pizza kits or Girl Scout cookies or popcorn or anything like that, you know, you charge a certain price for the item you're selling, and a person pays you, the amount that they owe for everything that they buy off you, but that doesn't necessarily mean that that's how much money you get to keep for whatever fundraiser or what have you that you're raising money for. The money that you bring in before the bills are paid, as I like to say, is the revenue. Now it says here, if X units of the item are sold at a unit price P, then we have a formula for revenue. It's X times P. Okay, number of units times price per unit will give you the total money brought in. Now the law of demand says this. It says if one of P or X increases, then the other decreases. So going back to this revenue function, if the quantity increases, then the price can go down. Whereas if the quantity decreases, then the price can go up. And the reason for that is because you might have a target revenue in a certain time period. So let's say you wanted to make a certain number of dollars in the month of February. If you don't have enough stock, then you'd probably have to raise the price of whatever you're trying to sell to meet that revenue goal. Whereas if you have so much stock that you need to free up space, on your shelves to sell other things, then you might lower the price because, the lower the price, the more business you tend to attract. Now, a relationship between price and quantity sold in this section is given by, or is referred to as a demand equation. And I'm going to draw a little schematic over to the right. And what a demand equation is, it's an equation that relates the two variables X and P that's kind of independent of the revenue equation. And I'm going to use the equation given in this example to help me with this illustration. It says that the price P in dollars and quantity X sold of a certain product obey the demand equation, which is given by this guy. P equals -1/5 X plus 120. That right there is a linear equation and it has a negative slope. And this equation basically helps us determine what price we should mark our product at, depending on how many how many units we want to sell. And this equation right here is only good for the X values between 0 and 600. Okay, so you can kind of think of this as like the range of stock that they might have. They might have nothing to sell, or the most they can sell is 600. If you were to plot this price equation using only these specific values of X, there would be a y-intercept and there would be an x-intercept. And because it's a line with negative slope, you'd have a segment of a line decreasing from left to right. Now going along the x-axis is the number of units, and going along the y-axis is your different price amounts. And basically think of it this way. As your quantity or your supply increases, you don't really need to have a very expensive price per whatever you're trying to sell. because you have enough of the stock to make up, the revenue that you would get should you have less stock, but still keep the price low. Now, if you went in the other direction where you don't have as much stock to sell, but you still need to meet a certain sales goal, then your price would go up. Okay, so if you have to make $1 million, in quarter one, but you don't have as much stock as you normally would, then whatever you're trying to sell typically goes up in price. So that's kind of what the law of demand does. Does that make sense? Yeah, pretty much. Yep. Yeah, kind of like an inverse relation there. Yep. If oil is in low supply, then prices typically tend to go up. Whereas if you have an abundance of oil, you don't really need to charge as much, so you can mark it down a little bit. Now, the questions here are what quantity X maximizes revenue, and what is the maximum revenue? Well, we don't really have a revenue function, at least not yet, okay? All we have is this demand equation, which can also be thought of as like a price adjusting equation. So there's a few things that we got to do here. Number one, we have to come up with the revenue equation, but it needs to be a function of x. And if we just use x times p, that's not going to work because there are two variables here, x and then p. The trick is to replace p with the demand equation. And in doing so, we'd have x times -1/5 x plus 120. And I'm going to distribute x to clear parentheses, and we would get -1/5 x squared plus 120x. Now the only variable used in this last line of math is x, meaning that the revenue can now be thought of as a function of x. And so the first step is to actually come up with your revenue function. And you'll notice that this is a quadratic function with an a value of -1/5 and a b value of 120. Now the fact that the value of a is less than 0 would mean that if we were to graph this revenue function, it would be a parabola that opens in which direction? So right, yep, looking at r of x, if we were to graph it, it'd be a parabola that opens down. So it should make sense that there is a maximum revenue. And that's going to occur at the vertex h comma k. So the second part here is to find the vertex. All right, can I kick that off to you folks? Find h comma k, and when you get those values, if you don't mind, type them into the chat. That'd be greatly appreciated. Otherwise, I'll check in with you in just a couple minutes. All right, so h is given by negative 120 divided by 2 times negative 1/5. Really critical to use extra set of parentheses in the denominator here. All right, who here got 300? Cool. Now, this represents the number of units that have to be sold, and we don't really know what they're selling. So, but I will include this along with it, just so that we don't confuse this with a dollar amount. So 300 units would maximize the revenue. To figure out what that maximum revenue is, we find K, which is going to be given by R of 300. So that'd be negative 1/5 times 300 squared plus 120 times 300. And I don't know about you guys, but I got 18,000 as the max revenue. All right, anybody getting something different? All right, so that's our max revenue. And 300 units is what we would need to sell in order to achieve this revenue. All right, questions, comments, concerns, winning lotto numbers? You guys still with me? If so, let's put a little bit of a different spin on a very similar example. Our price P in dollars and quantity X sold obey the demand equation, which you'll notice the roles of X and P are reversed. This time it says X equals negative 7P plus 700. So this is an example of a demand equation where we can figure out how many units we want to sell based on different price amounts. Okay, so we can play around with different pricings and figure out how many of the product, how much of the product we would need to sell. And the reason why it's expressed this way versus P equals is because of part A. Part A wants us to express the revenue function as a function of P. So they're looking for R of P instead of R of X. Now we'll start out the same way. Revenue is quantity times price per unit. And we only want the variable P involved in the equation this time, so we'll have to replace X. And we can replace X with the demand equation. So let's replace it with negative 7P plus 700. And then P is to the right. And I'm going to clear parentheses via backwards distribution of P to get negative 7P squared plus 700P. Now P is the only variable used at this point. So we can say that the revenue is a function of the price P. So far, so good? Now, what is the domain of this revenue function? The trick to figuring that out is to realize that to make some revenue, you're going to need some positive values for P. In certain cases, your product might be free, if you just want to get rid of it. So keeping in mind some real-world stuff, the price P should be greater than or equal to 0. You also need stuff to sell, but there are those times where you might not have any product to sell. So I'm going to put a condition on x and say that x should be greater than or equal to 0. Now keep in mind our independent variable is the variable p. Okay, we want r as a function of p. So we want to figure out what specific values of p can be used in this model. So far, we have that p is greater than or equal to 0. But noting that x should be greater than or equal to 0 as well allows us to take the demand equation and figure out a maximum value of p by solving this inequality. Now check it out. We can subtract 700 from each side to get negative 7p is greater than or equal to negative 700. And from there, we would divide by negative 7. And what do we have to keep in mind when we divide an inequality by a negative number? Yep, this is going to reverse direction. So this tells us that p should be less than or equal to positive 100. So p should be greater than or equal to 0, but at the same time be less than or equal to 100. That means for us is that p is trapped between these values, which I'm going to write that fact as a compound inequality. Okay, so the minimum price is 0, and the maximum price is going to be $100. And I think my math lab might want the interval notation version of this, so I'll provide that. For part C, I'm going to kick off to you folks. What price P maximizes the revenue? What is the maximum revenue? And then if you want, you can try this last part, but we'll definitely go over that together in a couple of minutes. Now, keep in mind that our revenue function is quadratic, okay? Highest power is 2. And the value of A is negative, specifically negative 7. Our value B is 700. So the fact that our value of A is negative would mean that there is a maximum revenue. Okay, so let me see if you can go ahead and figure out part C. If you want to attempt the last part of that problem, go for it. But we'll go over all of it together in just a couple minutes. All right, anybody want to offer what price P maximizes the revenue? Call that part one, I guess. $50, awesome. How'd you get that? All right. Yeah, let's keep in mind the context here. Along the x-axis going to be our different values of P. Along the y-axis are different revenues. Now we did establish that this would be a parabola facing down. So there is a maximum revenue that would be at h comma k. And the price P that gives us this maximum revenue is going to be indicated by the value of h. So for number one, we should be calculating h, which is negative b over 2a. B is 700. A is negative 7. Again, don't forget to use the extra set of parentheses. And we should get 50. All right. So that would be a particular value of P. And very good, Daniela. Appreciate that. Number two, the second part here, what is the maximum revenue? And that's going to be indicated by our value of K, which to figure out K, we plug 50 into our revenue function. And when you calculate that, if anybody wants to confirm this with me, 17,500. Very good. That's our max revenue. The third and final thing is how many units are sold at this price. A couple ways you can do that. You can use the revenue equation, R equals X times P. We have the value of R and P, so we could just solve an equation, or we could use the demand equation, X equals negative 7P plus 700. All right, so which route do you guys want to take, X times P or the demand equation? First or second, which one do you want to use? I'll go with, yeah, okay, we can do that. We'll use this one. Now keep in mind that $50 is what we should be charging. So it's negative 7 times 50 plus 700. And the number of units you can expect to sell to get this maximum revenue when the price is 50 is 350 units. All right, is this all making sense? Dollars and cents? So we'll move on to our last part. They want us to graph R and then find the prices for which the company should charge to earn at least $14,112 in revenue. So here's the strategy. We're going to type in two equations. Y1 is going to be our revenue function. Now there is no variable P key in our calculators, so we'll have to use X in place of P. But there should be a second equation as well. And that second equation is going to be based on this value of 14,112. In fact, that's what we'll type in to Y2. But there should also be some window setting changes just so that you can see everything that we need to in order to solve this. Xmin and Xmax are going to be based on our domain values. Keep in mind the minimum value of P is 0 and the maximum value of P is 100. So that's how I'm getting 0 and 100, and I'll go by tens along the x-axis. Hopefully the revenue is never negative, but it is possible that the revenue is 0. So I'm going to set the Y-min at that value. And then we know that the maximum revenue is 17,500. So for Y max, let's maybe overshoot that a little bit. Maybe do 20,000. And if we want, we can go by 1,000s on the y-axis. Okay, so go ahead and take a moment to type these two equations into your graphing calculator, as well as make these window setting adjustments, and I'll do it alongside of you guys. All right, so that's what we should have in the y equals menu. And now the window setting adjustments. All right, so that's our window setting adjustments. Let's go ahead and press graph. All right, we've seen this. Sweet. If we wanted to, we could use our graphing calculator to verify our maximum value, but we won't do that, just in the interest of time. Let me go back to the notes. I'll sketch these two graphs out. It's a x max of 100, y max of 20K, then y2. So this horizontal line crosses the y-axis at 14,112. And our blue graph is the revenue function. Based on what the instructions are asking for, it says find the prices at which the company should charge to earn at least 14,112 in revenue. That can be formulated as follows. R of P is greater than or equal to 14,112. In the context of Y1 and Y2, this is asking us to figure out what values of X force Y1 to be greater than or equal to Y2. And when we have diagrams like this, the greater than symbol requires us to find any part of Y1 that's above Y2. And there is a part of Y1 that's above Y2, and it would be this part of the hill. So the prices that correspond to this piece that I have highlighted in yellow would be all of those that are between these 2 points of intersection. Okay, I'm going to go underneath each point of intersection and put a tick mark. Okay, because the first tick mark is the minimum price, the second tick mark is the maximum price in order for the revenue to be at least 14,112. So your mission right now, should you choose to accept it, is to use the intersect feature to figure out where these 2 points are at. And then we'll steal the x coordinates of those 2 points and that'll help us formulate our answer to this problem. Okay, so go ahead and see if you can take the next couple of minutes to figure out the location of these points of intersection. I'll check in with you once that's taken care of. Yep, I concur with that. So the first point of intersection should be at 28, comma 14,112. That 28 would represent the minimum price for which to start earning a revenue of at least 14,112. And then the next one is going to be at 72, comma 14,112. So this would be our maximum price. So the prices for which the company should charge to earn at least 14,112 in revenue are those that are between 28 and 72 inclusive. So we kind of have this scaffolded a little bit. The company should price between a minimum of $28 and $72. Now, if you're wondering why the revenue goes down as you increase your price, it has to do with the demand equation that's working behind the scenes. Okay, our demand equation is this guy right here, and it has a negative slope. So as you increase P, the value of X decreases. Okay, and your X's will decrease, will eventually decrease so much that it begins to impact your revenue. So that's why we have revenue functions in this section, typically as parabolas opening down, because they're usually built off of demand equations. And keep in mind, the law of demand says that as one increases, the other decreases. And when the second of those two values, either X or P, decreases, it begins to decrease so much that you stop bringing in, as much money as you would hope to. So just in case anybody was wondering. And now, our last thing is going to be to work with data. Specifically, something called bivariate data, meaning that we have numbers, measurements that are related to two different variables. So I go into detail on how you can find a linear model in the videos for section 4.2. As mentioned at the beginning of class today, I'll be reviewing some of those techniques because there's a lot of similarity between what you saw in 4.2 compared to what we're going to do right now. So we're going to take this information, this data here, which is on a study between the age of women and the birth rate that corresponds to the age. Now, I don't know, like where, the study has taken place or anything like that, but the author does cite his source down there. So if we look at the values in the table, maybe starting with, the age A of 16, there's a birth rate of 14.1. So when they did this study, they took a look at, all the 16-year-olds, whatever region they were studying this at, and they found that, there were on average 14.1 births, for every, 1,000 people. And then the rest just kind of follow suit there. And you'll notice as the age increases, the birth rate increases. And we actually have kind of like a peak birth rate in this table of 106.5, corresponding to the age bracket of 27-year-olds. And then it decreases. Okay, so it goes from 106.5, drops down to 97.3, and then it drops down pretty significantly as you increase in age here. And there's a lot of reasons as to why that might be, but I'm going to kind of leave the speculation out and just illustrate how we can create this table in our graphing calculator and then look at something called the scatter diagram, which is basically a plot of these points. And we can also use the graphing calculator to help us construct a quadratic function that would best model this data. In part A, they want us to draw a scatter diagram of the data where they want age to serve as the independent variable, which means that the birth rate is going to be the dependent variable. One thing to always keep in mind is that the independent variable is going to go into what's called a list, and there are going to be two lists that we work with. This is going to go into the L1 list. So all of these values in this age column will be entered into our calculator into the L1 part of a table. And the dependent variable B, all these values will get entered into an L2 column of our table. And let me show you how to do that. I'm going to go back to the home screen. And let's press the Stat button. In the first column, the Edit column, option 1 says Edit. Go ahead and press Enter. It brings you to a menu where we have 3 columns, L1, L2, and L3. The most important ones, of course, are L1 and L2. Does everybody have an L1 and L2 column in their calculator? Okay. No? All right, so Kevin, let's hit. Okay, so Kevin, let's press Stat. And we'll go to option 5. Press Enter. And then press Enter one more time. Go back to Stat. Option 1. You got it. So we're going to type in all of the age values from our table in L1. So 16, 19, and be sure to press Enter each time, especially when you get to the last value in that column. Sometimes your calculator forgets to save it. So you can bypass that by pressing Enter. To get to the L2 column, simply press your right arrow button, and we'll type in all of the different birth rates B. Oops. Oh. There we go. Okay. Let's go to the y equals menu. And we'll get rid of all these equations from our last problem. Now, I'd like you folks to go up to where it says plot 1 and press enter. And come back down to Y1. This should be highlighted in black. And when it's highlighted in black, it tells the graphing calculator that you're going to have it plot a table of values. So whenever working with data, you need this to be highlighted in black for your scatter diagram. And the best scatter diagram viewing window is going to be found by pressing zoom and choosing option 9. Okay, so you press zoom and scroll down to where you get to where it says zoom stat. Okay, go ahead and press enter. And that would be our scatter diagram. Are you guys getting a similar looking graph? Anybody need me to repeat any of that? Okay, yep. Do you have the data entered into the L1, L2 column? Okay, so you go to y equals, and you scroll up to where it says plot 1, and you want to press enter, and jump back down to Y1 and make sure that it's plot 1 is highlighted in black. Is yours highlighted? Okay, now press zoom and select option 9. Oh, it's awesome. No problem. Now for the answer to part A, where it says draw, or when it says draw a scatter diagram of the data, just a rough sketch of the points that you're seeing is good enough for me. So just try to recreate those little boxes which represent the data as best as you can. It doesn't have to be 1000% accurate here. And keep in mind that the independent variable is the age A. So I'm going to label the x-axis as the A-axis, and then the y-axis is going to be representing the different birth rates. And as you can see, the birth rates go up until they kind of peak, and then they begin to go down as the age continues to increase. So where it says what type of relation appears to exist between age and birth rate, well, it's definitely not linear, which leaves only one option left for the type of relation, and that would be a quadratic relation. This definitely looks like, the shape of a parabola, more or less. So quadratic relation. And the last thing that we'll do today is part B. I want to show you how to get the quadratic function that can be used to approximate these data values. And then I'll include the solution to part C on Blackboard. So what you're going to do to get the quadratic function is you'll press stat again. You'll arrow over to the calc column, and then you'll select option 5. Now for section 4.2, where it wants a linear model, you select option 4. Okay, and it's nice enough to give you the format of the linear function, but we want a quadratic function, so we're going to select option 5 where it says quad reg, which reg is short for regression. Go ahead and press enter, and if you have a TI-84, you'll see a menu similar to this, but if you have a TI-83, you're probably back at the home screen. So hang tight, all my TI-83 folk. If you have a TI-84, make sure that this says L1 and this says L2, and then the next two rows are blank. Once that's all taken care of, scroll down to calculate. And for those of you that have a TI-83, we've caught up to you. Let's everybody, whether you have an 83 or 84, press enter. And we should be seeing something like this. In the top row, it tells you the format of the quadratic function that they're assuming you'll write it in. And then it gives you the values of a, b, and c for that quadratic function. Now sometimes you might see a row for r squared, and if you're seeing a row for r squared, don't freak out about it. Yep, so r squared is a value that's going to be between 0 and 1, and the closer that r squared is to 1, the better the model is for the data. The graphing calculator does produce the best model possible for the data, and the value of r squared, as well as the value of r, if you watch the 4.2 videos, they basically give you a level of confidence in using these functions to approximate the data values. So generally speaking, the closer to 1 that we are with r squared, the better. And with regard to linear regressions, the closer you are to 1 or negative 1, the better the function. Okay, so 0.963. Yep, so I'll be including some videos as to how you can find the r and r squared values. I'll put them into the folders. But for now, what I'd like to do is just write our quadratic function using these values of a, b, and c. And if there are no rounding instructions provided, then you'll want to round to 4 decimal places. Okay, so with that said, our value of a is approximately negative 0.5471. Our value of b, approximately 31.1900. And then c is roughly negative 342.2177. And are you guys getting the same values for a, b, and c? Okay. So this will basically get folded into our quadratic function, which you have a couple of ways of writing that. You can write it as f of x if you want, or you can write it as b of a. Okay, b of a is just the usage of a and b, the variables that they're using in this table. So just put these values into your function. Okay, that would be one version of it. And of course, you could use a instead of x to get a function that uses variables more specific to the problem. Woo! All right, so like I said, I'll include the solution to part C on Blackboard, but do you guys have any questions for me regarding any of this material?